All right, we're looking at a quick example of Euler's method here. So estimate the solution, the following solution using Euler's method with n equals 5 steps over the interval from t equals 0 to 1. So we're using the equation, it's not typed up here, so I'm writing it out. Y prime equals 3t minus y, and y of 0 is equal to 1. So what you'll notice here in this case, the differential equation refers to the y value in the equation, and that's okay. The way that I like to do this is by setting up a table. So I start with the independent variable, and then I'm just going to write out all the steps or all the points that I'm going to have to go through. So if I want 5 steps from 0 to 1, that means each step is going to be 0.2. So I start with 0, then the first step will take me to 0.2, the second step will take me to 0.4, the third step will take me to 0.6, the fourth step 0.8, and the fifth step 1.0. Then I create a column here for my y values, or for my dependent variable values. In this case, I know that y of 0 equals 1. I know the initial value. Then I'm going to create a column where I put in the slope. Then I'm going to create a column. This one's optional. If you want, you can put a delta x if that's helpful for you to visualize things. I find it helpful about half the time. It depends on how complex the problem is. And then I'm going to put a column for delta y. And this way I can kind of just work left to right and then jump down to the next line. So for 0, 1, if I plug those into my equation, y prime is equal to 3 times 0 minus 1. That means that y prime here is negative 1. My step size here is going to always be the same. By the way, with Euler's method, these don't have to always be the same, but I do believe that the AP Calculus, you only do it for uniform step sizes. So then delta y is delta x times the slope, so I know that delta y is negative 0.2. Now negative 0.2, or now I know my next point is going to be 0 plus delta x, 0.2, 1 plus delta y, 0.8. Then I can easily come and plug in my next value, 3 times 0.2 minus 0.8. And at this point, I'm going to be checking against, I had done these before, so I'm not actually going to start solving them. But the next value, and you can double check these if you want, will be 0.2. 0.2 times 0.2 is negative 0.04. I add 2 to my t to get this value. I add negative 0.04 to 0.8 to get 0.76. The next slope that you'll calculate will be 0.44. Multiplying across, we get 0.088. Adding 0.2 to my t value gives me, sorry, this should have been t, will give me 0.6. Adding 0.088 to 0.76 gives 0.848. And then if you calculate the slope based off of 0.6 and 0.848, you should get 0.952. 0.952 times 0.2 is 0.1904. Adding these points to get the next value, I get 1.0384. Adding finding the new slope should be 1.3616. And again, I encourage you to try these yourself. I'm just writing them out so you can double check the work. And then a delta y here of 0.27222. And now for our final approximation, I don't actually have that one written down. 1.0384 plus 0.2722 is 1.3106. So y of 1 is approximately 1.3106. So this is the idea behind Euler's method. It's just a repeated process like this. If you have any questions, let me know, but hopefully that tracks pretty closely.